Somewhere in the vast, silent expanse of the cosmos, a galaxy spins with secrets we're only beginning to uncover. NGC 1300 isn't just another swirl of stars. It's a cosmic puzzle box, a barred spiral galaxy where the rules of physics seem to bend and twist in ways that leave even the most seasoned astronomers baffled. Picture this, a sprawling celestial structure, its arms stretching across 130,000 light-years, dotted with phenomena so strange they defy explanation. From rogue black holes lurking where they shouldn't be to unexplained pulses of energy that flicker like cosmic Morse code, this galaxy is a stage for some of the universe's most mesmerizing performances. What if I told you that within NGC 1300 there are whispers of forces we don't yet understand, forces that challenge everything we think we know about how galaxies behave? Imagine entire star clusters vanishing without a trace, or regions of space where time itself seems to stutter and slow. These aren't scenes from a science fiction thriller. They're real, documented mysteries happening right now, millions of light years away. And today, we're diving deep into 25 of the most jaw-dropping, spine-tingling enigmas this galaxy has to offer. Each one is a reminder that the universe is far stranger, far more unpredictable than we could ever imagine. This isn't just a tour of cosmic oddities, it's an invitation to witness the edges of human knowledge. Think of it as standing on the shore of an endless ocean, watching waves of discovery crash against the rocks of the unknown. Some of these phenomena might hold clues to the birth of galaxies, while others could rewrite the textbooks on dark matter or quantum physics. But one thing's for certain, by the time we're done, you'll never look at the night sky the same way again. So let's set sail into the depths of NGC 1300, where every twist and turn reveals another piece of the universe's grand, unsolved mystery. At the heart of most galaxies, there's a monster lurking, a supermassive black hole, an unimaginably dense beast anchoring everything around it with gravity's iron grip. But NGC 1300 isn't playing by the rules. When astronomers pointed their telescopes toward its center, they expected to find the usual cosmic heavyweight. Instead, they were met with silence, a void where a supermassive black hole should be. It's like lifting the hood of a car and finding the engine missing. Galaxies just don't work this way. Or do they? One theory suggests the black hole isn't gone, it's just sleeping. Black holes, when they're not actively devouring nearby gas and stars, can enter a quiet phase, emitting almost no detectable radiation. Imagine a bear in hibernation, still there, just invisible to the casual observer. But here's the twist, even dormant black holes leave gravitational fingerprints, warping the orbits of nearby stars. Yet in NGC 1300, those telltale signs are frustratingly faint, as if the galaxy is deliberately hiding something. Then there's the dust theory. Picture a thick cosmic fog, swirling clouds of debris and gas so dense they could be masking the black hole's usual fireworks. It's not impossible our own Milky Way's central black hole is often shrouded in dust. But even then, advanced instruments can usually pierce the veil. NGC 1300's core, though, remains stubbornly opaque, resisting every attempt to reveal its secrets. But what if the truth is even stranger? Some researchers speculate this galaxy might have ejected its black hole entirely, a cosmic game of intergalactic dodgeball. When galaxies collide, their central black holes can merge, releasing such violent gravitational waves that the newborn black hole gets kicked clear out of the galaxy. Could that have happened here? If so, where is it now? Floating in the vast emptiness between galaxies, a dark wanderer without a home. Every unanswered question about this missing black hole forces us to reconsider what we know about galactic evolution. Maybe supermassive black holes aren't as universal as we thought. Or perhaps NGC 1300 is showing us a new phase in a black hole's life cycle, one we've never witnessed before. One thing's certain, this cosmic whodunit is far from over. Now let's turn our gaze from the galaxy's enigmatic core to its outer reaches, where another bizarre spectacle unfolds, the phantom spiral arms of NGC 1300. These ghostly structures flicker in and out of visibility like a cosmic magic trick, leaving astronomers scratching their heads. One moment, a telescope captures a sweeping arm of stars and gas in perfect clarity. The next observation, it's as if that entire section of the galaxy has been erased from the cosmic chalkboard. One leading explanation points to vast clouds of interstellar dust, thick, inky veils drifting between us and the galaxy. Think of it like trying to spot a streetlight through heavy fog. The light's still there, but the dense particles scatter and absorb its glow, rendering it nearly invisible. In NGC 1300, these dust clouds could be so colossal and chaotically distributed that they selectively cloak entire segments of the spiral arms from view, depending on the angle and wavelength of observation. But here's where it gets weird. Some of these vanishing acts don't align with typical dust behavior. In certain cases, the missing regions reappear in infrared observations, dust's usual giveaway, while remaining stubbornly absent in visible light. That's like expecting to find fingerprints at a crime scene, only to discover the suspect wore gloves, but left behind a glowing neon signature instead. It doesn't add up, and that's exactly why some researchers are exploring far wilder possibilities. Enter gravitational lensing, the universe's funhouse mirror. Einstein's theory tells us massive objects warp spacetime, bending light around them. If an unseen object, say a rogue cluster of dark matter or even a wandering black hole, drifted between us and NGC 1300, it could distort our view, smearing or erasing parts of the spiral arms like a cosmic paintbrush. The kicker, unlike dust, lensing wouldn't leave behind the usual infrared breadcrumbs, making it a stealthy culprit for these disappearances. The debate among astronomers is anything but settled. Purists argue for simpler explanations, like transient dust storms on a galactic scale. Others whisper about more exotic physics, perhaps a previously unknown interaction between dark matter and visible structures. Every time a new observation contradicts the old models, the mystery deepens. It's as if the galaxy itself is playing hide and seek, daring us to rethink how spiral arms form, evolve, and occasionally vanish without a trace. Most galaxies with a bar structure, a thick band of stars cutting through their center, follow a predictable pattern. The bar acts like a cosmic traffic conductor, funneling gas and stars toward the core in a slow, steady rhythm. But NGC 1300's bar is different. This one crackles with instability, flickering in brightness like a faulty street lamp while its shape contorts in ways that defy conventional models. It's as if the galaxy's spine is made of rubber, bending and warping under some invisible force. The first clue something was amiss came when astronomers noticed the bar's brightness wasn't just fluctuating, it was doing so asymmetrically. One side would flare up while the other dimmed, like a seesaw with an unseen weight on one end. Normally, a galactic bar's luminosity stays relatively stable, its stars orbiting in a synchronized dance. But here, the motion is chaotic, with entire clusters speeding up or slowing down without warning. Imagine a whirlpool where sections of the water suddenly reverse direction. That's the level of disruption we're talking about. One compelling theory points to dark matter, the universe's most elusive architect. If a clump of dark matter passed through the bar, its gravity could tug on stars like an invisible hand stirring a pot. Unlike ordinary matter, dark matter wouldn't emit light or collide with objects, leaving no trace except gravitational ripples. This might explain the erratic motions, stars being jerked around by something we can't even see. But there's another possibility lurking in the shadows. NGC 1300 might not be alone. Some simulations suggest the bar's instability could be the aftermath of a galactic near miss, a smaller galaxy brushing past like a ship in the night, its gravity disturbing the bar's structure. The intruder could be too faint to spot now, lost in the glare of the main galaxy or disguised as a harmless cloud of gas. Yet its gravitational fingerprints remain etched into the bar's chaotic sway. The plot thickens when you consider the bar's unusual composition. It's not just old red stars, the usual residents of galactic cores, but younger, bluer stars too, scattered like unexpected guests at a formal dinner. These youthful interlopers suggest bursts of recent star formation, possibly triggered by the same upheaval causing the bar's instability. Picture a tranquil river suddenly churned by a landslide. The turbulence creates new eddies, just as the bar's disorder might birth fresh stars. Every fluctuation in that bar forces us to rethink how galaxies evolve. Maybe instability isn't a flaw, it's a feature, a sign of hidden dynamics shaping the cosmos in ways we're only beginning to grasp. Whatever's stirring the pot in NGC 1300, one thing's clear: this isn't just a bar. It's a cosmic mystery written in starlight. Deep in the silent outskirts of NGC 1300, radio telescopes have picked up whispers from the void, mysterious pulses of energy that shouldn't exist. These ghostly radio emissions flicker like a distant lighthouse, broadcasting from regions of the galaxy where nothing visible could be producing them. No pulsars, no quasars, no supernova remnants, just empty space crackling with invisible energy. It's as if the galaxy itself is humming a tune we can't quite decipher. The first detection sent astronomers scrambling. These weren't the steady, predictable signals of known objects but erratic bursts, sometimes vanishing for months before reappearing without warning. Imagine tuning your radio to static and suddenly catching a snippet of music only to have it fade before you can identify the song. That's the maddening tease of these emissions. They defy the usual rhythms of cosmic radio sources. One leading suspect: hidden neutron stars, the dense corpses of exploded suns. These cosmic cinders can spin wildly, shooting beams of radiation like interstellar lighthouses. But here's the catch: neutron stars typically leave X-ray or gamma-ray fingerprints, yet NGC 1300's mystery signals shine only in radio wavelengths. It's like finding a flashlight that emits heat but no light. Some researchers speculate these could be radio-only neutron stars, a breed we've never seen before. Their other emissions somehow muffled by surrounding debris or magnetic fields we don't yet understand. Then there's the dark matter angle. What if these waves are the echo of something far stranger? Certain theories suggest dark matter particles, when they collide, could release energy in the form of radio waves. If true, these faint signals might be our first glimpse of dark matter interacting with itself, a shadow universe flickering into view. Picture trying to study a conversation by listening only to the reverberations in a closed room. The words are muffled, but the rhythm hints at something alive in the darkness. But the oddest possibility of all: these emissions might not originate from any object at all. Some models suggest they could be the aftermath of cosmic strings, hypothetical flaws in spacetime's fabric left over from the Big Bang. Like a plucked guitar string vibrating long after the musician's hand has left it, these primordial defects could ripple through the galaxy, shaking the electromagnetic field as they pass. The idea straddles the line between physics and philosophy, forcing us to ask, could spacetime itself be singing to us? Every flicker from NGC 1300's dark corners challenges our cosmic map. Whether it's undiscovered stellar remnants, whispers from the dark side of the universe, or spacetime's own vibrations, one thing's clear: this galaxy is broadcasting secrets we're only beginning to decode. And the more we listen, the stranger the signal becomes. Somewhere in the spiral arms of NGC 1300, stars are being born where they shouldn't be, vast stellar nurseries igniting in the cosmic equivalent of a ghost town. These aren't the slow, methodical star-forming regions we're used to seeing. These are violent, sudden bursts of creation, hundreds of stars flaring to life in regions that by all accounts should be stellar deserts. It's as if someone scattered matchsticks across dry tundra, and instead of smoldering, they erupted into bonfires. The first clue to this enigma came when astronomers noticed pockets of intense ultraviolet light, the signature of massive young stars where telescopes had previously mapped only empty space. These weren't just a few new stars, they were full-fledged starbursts, events usually reserved for galaxies colliding or gas clouds collapsing under their own weight. Yet here they were, appearing like clockwork every few million years in the galaxy's quiet outskirts, far from any obvious trigger. One explanation points to dark matter's invisible hand. Clumps of this mysterious substance, woven through the galaxy like an unseen scaffold, could be acting as gravitational traps. Picture a spider's web strung between tree branches, invisible until dew droplets gather along its strands. Similarly, dark matter's gravitational pull might silently accumulate hydrogen gas over eons, compressing it until, boom, the gas reaches critical density and explodes into stars. If true, these starbursts could be our first tangible evidence of dark matter's architecture on a galactic scale. But there's a rival theory with its own compelling twist. NGC 1300's serene appearance might be an illusion, a cosmic facade hiding a violent past. Computer simulations suggest these starbursts could be aftershocks from a long-ago galactic merger, like ripples from a stone tossed into a pond. When two galaxies graze each other, their gravitational dance sends shockwaves through their gas reservoirs. These waves can take millions of years to travel outward, finally triggering star formation far from the collision site. We might be witnessing echoes of a cataclysm so ancient, its scars have all but faded from view. The smoking gun, strange metallicity patterns in the newborn star's chemical fingerprints that don't match the galaxy's usual composition. Some of these stellar infants are rich in elements typically forged in galactic cores, hinting their gas might have been hurled outward during some forgotten upheaval. It's like finding tropical fruit growing in a temperate forest. The seeds had to come from somewhere far away. What makes this mystery so thrilling is its defiance of the usual rules. Starbursts aren't supposed to happen in isolation, yet NGC 1300 keeps churning them out like cosmic popcorn. Whether it's dark matter's subtle influence or the ghostly aftershocks of an ancient collision, one thing's clear: this galaxy is rewriting the playbook on how stars are born. And each new stellar firework might be a clue to forces we've only begun to imagine. Galaxies like NGC 1300 should be surrounded by a bustling entourage of dwarf galaxies, small cosmic companions that orbit like moths around a flame. Yet when astronomers mapped its neighborhood, they found a ghost town. The missing dwarfs present a puzzle that could unravel our understanding of galactic evolution. Where did they go? Were they swallowed whole, or did they never form at all? One possibility is as grim as it is fascinating. NGC 1300 might be a cosmic cannibal. Larger galaxies often grow by consuming smaller ones, tearing them apart with tidal forces until only scattered starlight remains. Evidence for this lies in stellar streams, river-like formations of stars winding through the galaxy's outskirts, the dissolved remains of past meals. But here's the catch: those streams should be everywhere if dozens of dwarfs were devoured. Instead, NGC 1300's halo is suspiciously clean, with only whispers of past feasts. It's as if a lion sat down to dinner but left no bones behind. Then there's the dark matter dilemma. Dwarf galaxies rely on dense pockets of dark matter to hold their stars together. If NGC 1300's dark matter halo is oddly smooth, lacking the usual clumps that act as galactic nurseries, dwarfs might never have formed in the first place. Think of it like trying to build sandcastles on a windswept beach. Without sheltered dunes, the structures never take shape. Some simulations suggest this could happen if the galaxy's dark matter was heated up long ago, perhaps by a close encounter with another massive galaxy, scattering the dense nodes needed to birth dwarfs. But the most tantalizing theory, the missing dwarfs might be hiding in plain sight. Ultra-faint galaxies, so dim they blend into the cosmic background, could lurk undetected. Recent surveys have spotted a handful of these ghostly objects in other galaxies. Their stars spread so thin they resemble fog more than fire. If NGC 1300's companions are similarly elusive, our telescopes might just need time and sharper eyes to spot them. This isn't just a census problem. The absence of dwarfs challenges the very model of how galaxies assemble. If dark matter behaves differently here, or if mergers leave fewer traces than we thought, our cosmic blueprints might need rewriting. Every empty patch of sky around NGC 1300 whispers a question. Are we missing pieces of the puzzle, or is the puzzle itself more complex than we imagine? In the swirling heart of NGC 1300, two colossal vortices of gas spin in perfect opposition, like cosmic whirlpools locked in an endless dance. These twin maelstroms, each stretching thousands of light years across, defy the usual rules of galactic weather. Gas clouds in a barred spiral should flow uniformly, steered by the galaxy's rotation. But here, one vortex churns clockwise while its mirror image counterpart spirals counterclockwise, creating a turbulent boundary where their forces collide. It's as if the galaxy took a deep breath and exhaled two storms in opposite directions. The mystery deepens when you consider the vortices' unlikely location. They're not out in the chaotic spiral arms where collisions and star formation might stir up such chaos, but near the galaxy's eerily quiet core. Without the usual triggers, no nearby supernova, no visible black hole activity, their existence becomes a cosmic whodunit. One theory suggests they're fossils of an ancient disturbance, like ripples frozen in a pond long after the skipped stone has sunk. Perhaps a rogue black hole or dark matter subhalo passed through the area millions of years ago, its gravity twisting the gas into these opposing spirals before vanishing without a trace. Then there's the mirror mystery, star clusters separated by vast distances, yet uncannily identical. Imagine walking into two different forests on opposite sides of the world, only to find the same arrangement of trees down to the last leaf. That's the level of precision we're seeing here, clusters with matching stellar populations, ages, and even chemical compositions, despite being hundreds of light years apart. The odds of this happening naturally are astronomically low, like rolling the same combination on a cosmic slot machine twice in a row. Could these twins be connected to the vortices? Some models propose that extreme gravitational shear, the same forces twisting the gas, might stamp out star clusters like cookies from a cutter, producing near-perfect copies. Picture a baker pressing dough into identical shapes. If the galaxy's turbulence is just right, it might mold star-forming gas into eerily similar configurations. But skeptics raise another possibility: data artifacts. Telescopes sometimes double faint objects due to calibration quirks or atmospheric interference. Yet follow-up observations with different instruments keep confirming the duplicates are real. Unless every telescope is conspiring to deceive us, we're left with two equally mind-bending options. Either NGC 1300 has cracked the code for cosmic copy-paste, or we're witnessing a new kind of physics, one where gravity weaves symmetry across scales we've never seen before. Whether it's hidden forces sculpting gas into perfect opposites or star clusters defying probability, one thing's certain: this galaxy refuses to play by the rules. And with every new discovery, the line between cosmic coincidence and universal law seems to blur a little more. Light behaves predictably, or at least it's supposed to. Traveling at a constant speed through the vacuum of space, it should take a precise amount of time for starlight to reach us from NGC 1300. But some stars in this galaxy are breaking the rules, their light arriving late, as if delayed by an invisible cosmic traffic jam. These aren't just minor hiccups, we're talking about anomalies measured in years, gaps that defy the laws of physics as we know them. Imagine shouting across a canyon and hearing your echo return a full minute later than expected. That's the level of contradiction astronomers are grappling with here. The first recorded instance came from a seemingly ordinary star cluster on the galaxy's outskirts. Observations taken a decade apart showed identical supernova explosions, except the second event's light arrived 8 years behind schedule. At first, scientists assumed it was a glitch, an error in the data, but then another star did it, and another. Each time, the light lagged by a different interval, as if something unseen was stretching the fabric of spacetime along specific sightlines. One explanation pulls from Einstein's playbook: warped spacetime. Massive objects like black holes or dark matter clumps bend the universe's fabric, forcing light to take detours. Think of it like a plane flying over a mountain range. The journey takes longer if it has to navigate valleys instead of cutting straight across. But here's the problem: NGC 1300's delayed light doesn't align with any known gravitational lens. There's no detectable mass along these paths, no cosmic boulders in the road. That's where cosmic strings enter the conversation. These hypothetical flaws in spacetime, thinner than an atom but unimaginably dense, could be lurking undetected. Picture a spider's silk thread stretched across a hallway, nearly invisible, but strong enough to snag a passing fingertip. If such a string intersected our line of sight to NGC 1300, it might warp space just enough to delay light without the telltale distortion of a lens. The idea straddles the edge of theoretical physics, but the math holds. A string's spacetime warping grip could slow light's journey without bending its path. Yet the most unsettling possibility is that we're seeing evidence of something even stranger: a breakdown in light's so-called universal speed limit. What if, under certain conditions, light doesn't travel at a constant speed? Quantum gravity theories suggest spacetime might be granular at the smallest scales, like a digital image pixelated under extreme zoom. Light moving through this foamy substrate could experience subtle drag, like wading through invisible currents. If true, these delays might be glimpses into the quantum structure of reality itself. Every delayed photon from NGC 1300 forces us to confront the uncomfortable truth. The universe's rules might have exceptions we've yet to discover. Whether it's hidden cosmic strings, uncharted physics, or something even more profound, one thing's clear: this galaxy isn't just showing us its secrets. It's teaching us how much we still have to learn. Stretching between NGC 1300 and its galactic neighbors, astronomers have detected faint, thread-like structures, invisible bridges woven from pure gravity. These filaments don't glow with stars or emit detectable radiation. Instead, they reveal themselves only by bending light from more distant galaxies, their immense mass warping spacetime like a hidden hand pressing down on a cosmic trampoline. It's as if the universe has strung an unseen highway system between galaxies, one that our eyes can't perceive but whose gravitational fingerprints are unmistakable. The discovery came when researchers noticed a peculiar pattern in the light from galaxies behind NGC 1300. Instead of the random distortions typical of gravitational lensing, the light was being bent in long, sweeping arcs, as if something linear and massive lay between us and those distant objects. Picture holding a magnifying glass over a piece of paper, but instead of a round lens, imagine a thin, straight rod bending the light in parallel lines. That's the signature these filaments leave, their gravity acting as cosmic fiber optic cables channeling starlight in unnatural directions. The leading explanation points to dark matter, the universe's most elusive architect. Simulations of cosmic evolution have long predicted that dark matter should form vast, web-like structures connecting galaxies, remnants of the primordial scaffolding that shaped the universe after the Big Bang. These filaments, often called the cosmic web, are thought to contain more than half the universe's mass, yet until now they've been nearly impossible to observe directly. NGC 1300's invisible bridges might be our first concrete evidence of this hidden infrastructure, the bones of the cosmos finally coming into view. But there's a twist. Some of these filaments appear too dense, too organized to fit neatly into standard models. Instead of the wispy, uneven strands predicted by simulations, certain sections seem almost braided, as if woven by an unseen force. One controversial theory suggests these could be dark matter rivers, regions where dark matter flows with unusual coherence, like water channeled through a canyon. If true, studying these structures could reveal whether dark matter interacts with itself in ways we've never imagined, perhaps even possessing a shadow version of viscosity or turbulence. Then there's the timing problem. These filaments seem to have persisted far longer than expected. Over billions of years, the cosmic web should have diluted as galaxies drifted apart, like strands of cotton candy stretching until they snap. Yet NGC 1300's bridges remain taut, as if reinforced by some unknown mechanism. Could there be a dark energy component counteracting the expansion of space within these filaments? Or are we seeing evidence of exotic physics where dark matter clumps differently on colossal scales? Every new observation deepens the intrigue. These filaments aren't just passive threads, they might actively shape galactic evolution. Gas and even entire star clusters could be funneled along these invisible highways, explaining why certain regions of NGC 1300 show sudden bursts of star formation with no obvious local trigger. Imagine a garden where water flows through buried pipes instead of rain. The plants flourish, but the source of their nourishment remains hidden. What's most exhilarating is what these bridges imply about the universe's hidden anatomy. If dark matter truly forms this intricate lattice, then galaxies aren't isolated islands, they're nodes in a vast, pulsating network connected by rivers of unseen mass. NGC 1300's filaments might be our first glimpse of the universe's true skeleton, a reminder that what we see through telescopes is merely the glittering surface of a far deeper mystery. And with every thread we trace, we're one step closer to mapping the invisible architecture of existence itself. Among the countless stars of NGC 1300, a peculiar group stands out not for their brilliance but for their bizarre behavior. These stars don't pulse with the steady rhythm of variables we're familiar with. Instead, they flicker erratically, their brightness dancing in patterns that mirror the unpredictable jitter of quantum particles. Astronomers call it the quantum twinkle, a phenomenon so strange it blurs the line between cosmic spectacle and potential physics-shattering discovery. At first glance, you might mistake these twinkles for ordinary noise, instrumental glitches, or atmospheric interference. But here's what's uncanny. The flickering follows distinct statistical patterns eerily reminiscent of quantum fluctuations. Imagine rolling a dice and getting the same improbable sequence over and over, not by chance, but as if the dice themselves were wired to obey a hidden rule. That's the level of order nested within this apparent chaos. Some stars in NGC 1300 dim and brighten in bursts that align with mathematical models of quantum tunneling, as if individual photons are leaking through barriers in spacetime itself. Skeptics argue it's all an illusion, a trick of the data. Telescopes, after all, are imperfect machines. Cosmic rays strike detectors, electronics hiccup, and even the interstellar medium can scatter light in ways that mimic false signals. But the more researchers clean their data, applying every known correction for noise, the more these quantum-like patterns persist. It's like listening to a staticky radio and realizing the static itself is carrying a melody. Then there's the radical interpretation. What if we're seeing quantum mechanics play out on a stellar scale? Normally, quantum effects vanish in large systems, drowned out by classical physics. But certain theorists propose that extreme gravitational fields like those near neutron stars or black holes could magnify quantum behavior, making it visible across light years. Picture a lab experiment where particles tunnel through walls, but scaled up to a star where entire layers of plasma might be hopping between energy states. If true, NGC 1300's twinkling stars could be cosmic Petri dishes, revealing quantum gravity in action. The debate is far from settled. Alternative explanations range from exotic stellar atmospheres, plasmas so turbulent they fractalize light emission, to undiscovered types of variable stars whose physics we've yet to model. One compelling middle ground: these stars might be interacting with dense dark matter clouds, their flickers caused by particles annihilating in waves against stellar surfaces. It's a cosmic version of fireflies blinking in sync, with dark matter playing the role of an invisible conductor. Every flicker from these stars forces us to confront a tantalizing question: are we seeing the limits of our instruments or the first hints of physics beyond our textbooks? Whether it's noise, new stellar behavior, or a quantum revolution playing out in real time, one thing's certain: NGC 1300 has a way of turning even the smallest glimmer into a beacon of cosmic mystery. Redshift should be simple. The farther and faster a star moves away, the more its light stretches toward the red end of the spectrum. It's one of astronomy's bedrock principles, the foundation of our cosmic distance ladder. But in NGC 1300, redshift has become a hall of mirrors. Stars in the same cluster, born from the same gas cloud and bound by gravity, are reporting wildly different redshifts, as if some are racing away while their neighbors stand still. It's like watching a flock of birds where half are migrating south and the other half insist on flying north, against every law of physics and common sense. First, the data itself defies logic. Take a trio of stars within a single nebulous cradle. One shows a redshift consistent with the galaxy's rotation. Another appears slightly blue-shifted as if falling toward us, and the third registers a redshift so extreme it would imply impossible velocities. If these measurements hold, at least one of these stars is breaking the cosmic speed limit, or our understanding of redshift is missing a critical piece. The discrepancies aren't small calibration errors either. We're talking about deviations large enough to rewrite orbital models for entire spiral arms. One explanation points to the interstellar medium, the thin soup of gas and dust between stars. Normally, light passes through it like a flashlight through mist, dimming slightly but keeping its color intact. But if pockets of this medium in NGC 1300 contain exotic particles or unusual magnetic fields, they could selectively tint starlight, skewing redshift measurements like colored filters on a camera lens. Picture sunlight passing through stained glass. The light's original color gets overlaid by the glass's hue. Similarly, mysterious interstellar filters might be warping our perception of these stars' motion. Then there's the dark matter hypothesis. If certain regions of the galaxy are laced with dense knots of dark matter, their gravity could bend light in ways that mimic redshift without actual motion. Imagine a car's horn distorting as it passes through a tunnel. The sound changes, but the car's speed doesn't. Likewise, dark matter's invisible hands might be stretching starlight as it travels to us, creating phantom redshifts where none should exist. But the most unsettling possibility: these stars might genuinely be moving in impossible ways. Some theorists speculate about rogue dimensions, subtle folds in space-time that could allow objects to briefly slip into higher or lower geometries, emerging with velocities that defy three-dimensional physics. Think of it like a billiard ball vanishing from one side of the table only to reappear on the other without crossing the middle, an effect that would look like magic to anyone watching. If spacetime itself is knotted or warped in NGC 1300, its stars might be threading needles we can't even see. The implications ripple far beyond this single galaxy. Redshift is our primary tool for measuring cosmic expansion, the very framework for dating the universe. If the rules are fluid here, how many other galaxies have we misjudged? Every contradictory measurement from NGC 1300 isn't just a puzzle, it's a potential crack in the foundation of modern cosmology. And until we solve it, we're left staring at a sky where the stars themselves seem to be whispering secrets we've yet to fully hear. Amid the swirling dust lanes and glittering star clusters of NGC 1300, three phenomena stand out as particularly mesmerizing: a nebula that sparkles like a cosmic jewelry box, a pulsar that broadcasts symphonies into the void, and a gravitational lens that bends reality into perfect circles. Together, they form a trifecta of mysteries that dance on the razor's edge between nature's artistry and something far more deliberate. First, the Diamond Nebula, a cloud of gas and dust where light doesn't just scatter, it shimmers. Unlike typical nebulae that glow in soft, diffuse hues, this region fractures starlight into sharp, prismatic flashes, as if filled with microscopic crystals. Spectroscopic analysis reveals the culprit: nanometer-scale silicate particles aligned with eerie precision, their atomic lattices arranged like a trillion tiny mirrors. Natural processes can create crystalline dust, but never in such abundance or uniformity. It's the difference between finding a grain of sand on a beach and stumbling upon a desert made entirely of cut gemstones. Could extreme magnetic fields or shockwaves from ancient supernova have orchestrated this cosmic jewelry? Or, as a fringe theory suggests, might these structures be remnants of a long-vanished civilization's technology, a fossilized artifact of astro-engineering on a scale we can barely fathom? Then there's the singing pulsar. Most pulsars are cosmic metronomes, their radio pulses ticking with mechanical regularity. But this one, catalogued as PSR J0318, defies the stereotype. Its emissions pulse in rhythmic sequences that mirror musical phrasing, not just simple beats, but patterns resembling melodies. When converted to audio, the pulses form repeating motifs akin to a 12-tone composition, complete with crescendos and rests. Mathematicians have analyzed these sequences and found fractal complexity, with smaller motifs nesting inside larger ones like a cosmic Russian doll. The leading natural explanation invokes spin-kick alignment, where the pulsar's rotation axis wobbles like a spinning top, modulating its beams into quasi-musical patterns. But the harmonies are suspiciously elegant. Could it be coincidence? Statisticians calculate the odds at roughly 1 in 10 million. Either we're witnessing the universe's most extravagant random performance, or something, or someone, is turning this dead star into a celestial broadcast. Finally, the gravity lens mirage. Gravitational lensing is common. Galaxies often warp background light into arcs or smears, but in one peculiar patch of NGC 1300, the lensing is freakishly precise. A cluster of dark matter, or perhaps an invisible exotic object, bends light from distant quasars into flawless Einstein rings, geometric halos so perfect they look machine-tooled. Even stranger, these rings occasionally pulse, their brightness flickering in sync across the entire circumference, as if the lens itself is vibrating. Traditional models struggle to explain such symmetry. Lenses should distort irregularly based on mass distribution. One radical paper proposes the lens might be a cosmic string loop, a hypothetical relic from the Big Bang shaped like a razor-thin, ultra-dense hula hoop. Its perfect geometry could explain the ring's precision, while quantum oscillations might account for the pulsations. The common thread: each phenomenon toes the line between the statistically improbable and the seemingly designed. Natural processes can explain them barely, but with assumptions that stretch plausibility. The Diamond Nebula's crystals might form in supernova shockwaves. If those shockwaves were unnaturally uniform, the pulsar's music could arise from rotation chaos, if that chaos somehow produced structured rhythms. The lensing rings might stem from a dark matter fluke, If dark matter clumps into shapes we've never observed elsewhere, it's the Goldilocks zone of cosmic weirdness, not blatantly artificial, but not comfortably natural either. Perhaps the most profound takeaway isn't whether these phenomena are natural or artificial, but how they expose the limits of our categories. NGC 1300 seems to delight in crafting spectacles that force us to ask, where does natural end and could something else begin? In this galaxy, even the dust sings, the emptiness draws perfect circles, and the light itself carries echoes of a universe far stranger than we've dared to dream. Deep within NGC 1300, an invisible storm rages, a hurricane of dark matter tearing through the galaxy at speeds that defy comprehension. Unlike ordinary matter, this hurricane leaves no visible wake, no swirling clouds of gas or glittering stars. Its presence betrays itself only through the subtle warping of space-time, bending the paths of light and tugging on stars like an unseen hand disturbing the surface of a pond. Astronomers call it the dark matter hurricane, and it's rewriting our understanding of how galaxies evolve under forces we can't even see. The first clues emerged when researchers noticed strange discrepancies in the motions of stars along one particular spiral arm. These stars weren't following the graceful arcs dictated by the galaxy's rotation. They were veering off course as if caught in a cosmic riptide. Mapping their trajectories revealed an eerie pattern, a narrow, high-speed current slicing through the galaxy, invisible but for the gravitational chaos left in its wake. Imagine walking through a quiet forest and suddenly feeling a gust of wind so strong it knocks you sideways, except there's no wind, no rustling leaves, just an inexplicable force shoving you forward. That's the paradox of this dark matter stream, all its fury with none of the usual storm's theatrics. What makes this hurricane so extraordinary isn't just its speed, estimated at nearly 500 kilometers per second, but where it came from. The leading theory suggests it's the shredded remains of a dwarf galaxy, torn apart by NGC 1300's gravity long ago. As the smaller galaxy was devoured, its dark matter, immune to the friction that slows ordinary matter, kept barreling forward like a bullet through smoke. Now, this relic stream surges through its predator, an invisible ghost of a meal the galaxy consumed eons ago. The implications are staggering. If dark matter can cluster into such dense, fast-moving rivers, it might explain some of NGC 1300's other oddities like the flickering spiral arms or the unstable galactic bar. Like a spoon stirring cream into coffee, this hurricane could be churning the galaxy's structure from within, redistributing mass in ways that trigger unexpected stellar births or deformations. Some simulations even suggest these streams might seed star formation by compressing gas pockets as they pass, lighting up new stellar nurseries in their wake. But the real mystery lies in the hurricane's longevity. Normally, gravitational interactions should disperse such a stream over time, smoothing it into the galaxy's broader dark matter halo. Yet this one remains razor-sharp, its edges delineated with unnatural precision. One controversial explanation invokes self-interacting dark matter, a hypothetical variant where these particles occasionally collide, creating a form of dark friction that keeps the stream coherent. It's the cosmic equivalent of a marching band maintaining perfect formation despite the chaos around them. If true, NGC 1300's hurricane could be the first tangible evidence that dark matter isn't just a passive scaffold but an active, dynamic player in galactic evolution. The deeper we probe, the stranger the picture becomes. Recent observations hint the hurricane might be rotating, not just moving in a straight line but twisting like a corkscrew as it travels. This spiral motion could be warping the galaxy's magnetic fields or even generating dark electromagnetic effects beyond our current physics. Picture a tornado made of shadow spinning silently through the cosmos, its influence felt but never seen. What's clear is this: NGC 1300 isn't just hosting a dark matter hurricane, it's being sculpted by it. Every star cluster nudged off course, every gas cloud compressed in its path leaves a fingerprint of this invisible tempest. And as we trace its invisible contours, we're glimpsing something profound. Dark matter isn't just the universe's hidden framework. It's a force that moves, clashes, and reshapes the visible cosmos in ways we're only beginning to fathom. In this galaxy, even the emptiness has a voice, and it's roaring. Tucked away in one of NGC 1300's spiral arms, a cosmic fountain erupts, not with water, but with particles moving at nearly the speed of light. This isn't just any cosmic ray activity. These are ultra-high-energy particles, each packing the punch of a major league fastball into a single subatomic speck. And the strangest part, there's no visible engine powering this relentless spray, no supernova remnant, no active black hole, not even a cluster of young, volatile stars. It's as if the galaxy itself has sprung a leak, and the universe's most energetic particles are gushing out from nowhere. For decades, cosmic rays were thought to be the exhaust fumes of violent cosmic events, supernova shredding stars, neutron stars colliding, or quasars belching plasma. But the particles from this fountain don't fit the usual profile. Their energies are off the charts, some exceeding 100 exaelectron volts, millions of times more powerful than anything produced in earthly particle colliders. If these rays were bullets, they'd pierce through a slab of lead as thick as a skyscraper without slowing down. The real puzzle, their paths don't trace back to any known celestial powerhouse. Point a telescope where these rays seem to originate, and you'll find nothing. Just empty space quietly defying the laws of physics. One theory sends us spiraling down the rabbit hole of primordial black holes, tiny, ancient relics from the universe's first second. Unlike their supermassive cousins, these black holes could be as small as an atom but as massive as a mountain, their gravity intense enough to shred passing particles into high-energy shrapnel. Imagine a cosmic woodchipper hidden in the void, silently grinding gas and dust into ultra-powerful rays. If such black holes exist in NGC 1300, they'd be virtually invisible to telescopes, yet capable of fueling this mysterious fountain. Then there's the dark matter angle. Hypothetical particles like WIMP, weakly interacting massive particles, could be colliding and annihilating in deep space, their deaths unleashing bursts of energy that morph into cosmic rays. Picture a minefield of invisible explosives detonating in slow motion over eons. The challenge: dark matter is supposed to be, well, dark, its interactions feeble by definition. But if some fraction of it decays or interacts more violently in this galaxy, it might explain the relentless particle barrage, but the plot thickens. Some of these rays arrive in synchronized bursts, like cosmic Morse code repeating at irregular intervals. That kind of pattern is tough to square with random processes like particle decay or black hole evaporation. It's the difference between rainfall and a fire hose. One follows the laws of chance, the other suggests a nozzle somewhere, even if we can't see it. Could there be an undetected particle accelerator the size of a solar system hidden in the galaxy's folds? Or something even stranger, a defect in spacetime itself? A cosmic crack where high-energy particles seep through from another dimension. Every detection from this fountain chips away at our understanding of particle physics. These rays might hold clues to forces beyond the standard model, or even signatures of a multiverse. But for now, NGC 1300 keeps its secret, showering the cosmos with particles that defy explanation, a reminder that sometimes the most profound mysteries aren't just about what's out there, but what isn't where it should be. Galaxies are supposed to have magnetic fields that follow predictable patterns, gentle spirals aligning with their arms, like invisible grooves on a cosmic record. But NGC 1300's magnetism is anything but orderly. Its magnetic fields don't just deviate from the norm, they twist into impossible knots, run perpendicular to the galaxy's spin, and occasionally flip polarity in abrupt, jarring transitions. It's as if someone took a hammer to this galaxy's magnetic compass, leaving it spinning wildly, pointing everywhere and nowhere at once. The first sign something was off came when astronomers mapped the galaxy's polarized light, a telltale sign of magnetic influence. Instead of the smooth, sweeping lines seen in most spirals, the data revealed jagged peaks and valleys, like a heartbeat monitor during a panic attack. Some regions showed magnetic fields stronger than those near active black holes, while others were eerily silent, as if the magnetism had simply switched off. The strangest feature, a vast corridor where the fields align perfectly against the galaxy's rotation, like a river flowing uphill. This defiance isn't just cosmetic. Magnetic fields shape how galaxies evolve, guiding gas flows, triggering star formation, even shielding regions from cosmic radiation. NGC 1300's chaotic fields could explain its erratic starbursts and vanishing spiral arms. But what's causing the chaos? One theory points to an ancient collision. If another galaxy grazed NGC 1300 millions of years ago, the gravitational turbulence might have scrambled its magnetic structure like a spoon through soup. The catch: most galaxies recover from such events, their fields resetting within cosmic timescales. This one's refusal to heal suggests something deeper is at play. Then there's the plasma paradox. Galactic magnetism is sustained by dynamos, churning motions of ionized gas that generate and amplify fields like a self-powered engine. But dynamos require symmetry. NGC 1300's plasma seems to move in broken, asymmetrical whirlpools. Picture trying to power a generator with water flowing in all directions at once. It wouldn't just fail, it might backfire spectacularly. Some researchers speculate that dark matter's gravity could be stirring the plasma indirectly, creating currents that defy conventional models. Others wonder if the galaxy's core, with its missing black hole, once housed a magnetic monster whose sudden departure left the fields unbalanced, like a spinning top losing its axle. The most tantalizing clue lies in the field scale. Magnetic anomalies usually localize a turbulent nebula here, a twisted arm there. But these distortions span thousands of light years, implying a force vast enough to wrangle the entire galaxy. One radical paper suggests NGC 1300 might be threaded with cosmic strings, hypothetical, ultra-dense flaws in spacetime. These strings, thinner than an atom but unimaginably heavy, could carry currents strong enough to warp galactic magnetism on a colossal scale. Think of it like running a live wire through a pile of iron filings. The string's influence would realign everything it touches, yet the truth might be simpler and stranger. Recent simulations show that under extreme conditions, plasma can develop memory, retaining traces of past magnetic states like a cosmic hard drive. If NGC 1300 endured multiple upheavals, collisions, quasar eruptions, dark matter storms, its plasma might be stuck in a feedback loop, replaying ancient disruptions like a broken record. That would make its magnetic field less a structure and more a palimpsest, layered with half-erased histories we're only beginning to decode. What's certain is this: every twisted field line challenges our understanding of how galaxies work. Whether it's unseen physics, hidden relics, or plasma with a mind of its own, NGC 1300's magnetism isn't just broken, it's rewriting the rules. And until we crack its code, we're left staring at a galaxy where the invisible forces refuse to follow the script. In the archives of astronomical observations, few events are as baffling as the phantom supernova of NGC 1300. A brilliant stellar explosion that flared into existence and then left nothing behind. Supernova are nature's grand finales, the spectacular deaths of massive stars that typically leave behind either a neutron star, a black hole, or a glowing nebula of scattered debris. But this one defied the script. In 2013, telescopes captured a blinding flash in one of the galaxy's spiral arms, a burst of light consistent with a Type II supernova, the kind caused by a collapsing stellar core. Yet when the dust should have cleared, revealing the aftermath, astronomers found only empty space. No remnant, no expanding shockwave, just silence where cosmic fireworks should have echoed. At first, researchers assumed it was a simple case of obscuration, perhaps thick interstellar dust had swallowed the supernova's aftermath. But infrared and radio observations detected no hidden debris, no telltale heat signature of cooling stellar material. It was as if the star had staged its own death, then vanished without a trace. The leading explanation, a failed supernova, a phenomenon theorized but never confirmed. In this scenario, a massive star's core might collapse directly into a black hole without the usual explosive fanfare, like a building imploding inward instead of bursting outward. The outer layers, deprived of the rebound shockwave from the core, would then quietly sink into the black hole's maw, leaving no trace. Yet even this theory strains to explain the phantom's brilliance. The initial flash matched the luminosity of a full-fledged supernova, not the dimmer flicker expected from a failed collapse. Some researchers speculate the star might have been enveloped in a previously undetected shell of gas, which amplified the explosion's light like a cosmic echo chamber. Others propose something far stranger, a quark nova, where the collapsing core doesn't form a neutron star but instead shatters into a soup of free quarks, releasing a burst of energy before vanishing into a black hole. Picture a firework that burns twice as bright, then winks out mid-explosion, its sparks snuffed by an unseen hand. The most tantalizing and unsettling possibility is that we witnessed a supernova triggered by dark matter. Certain exotic particles could accumulate in a star's core over millennia, poisoning it until sudden annihilation sparks a catastrophic chain reaction. Unlike normal supernova, such an event might leave no conventional remnant, its energy channeled into invisible particles rather than visible debris. It's the cosmic equivalent of a bomb that leaves no shrapnel, only shadows. What makes the phantom supernova so unnerving isn't just its defiance of expectations, it's the lingering doubt that our telescopes might have missed something fundamental. Could there be an entire class of stellar deaths that slip past our detectors, their signatures written in wavelengths or particles we've yet to discover? Every time we revisit that empty patch of sky, we're left with the same eerie question: did the star really vanish? Or are we just not seeing what it became? Scattered across NGC 1300, certain gas clouds defy the cosmic rulebook, not with their composition, but with their geometry. These aren't the usual chaotic blobs of interstellar material. They're eerily symmetrical, their edges tracing near-perfect geometric shapes, hexagons, tetrahedrons, even dodecahedrons, as if sculpted by an invisible hand. The most striking example, Cloud Gamma 9, floats in the galaxy's outer reaches, its hexagonal silhouette so precise it could pass for an engineering schematic. Nature abhors straight lines, they say, yet here, the universe seems to be doodling with a ruler. The discovery sent shockwaves through astrophysical circles. Gas clouds form through turbulence, gravity, and chance collisions, processes that should produce organic, asymmetrical forms, not crisp polygons. Imagine stirring cream into coffee and watching it spontaneously arrange into a perfect honeycomb pattern. That's the level of improbability at play. Skeptics argued it was a trick of perspective, dust lanes obscuring parts of the cloud to create artificial edges. But multi-wavelength observations only deepened the mystery. The shapes persisted in infrared, radio, even X-ray wavelengths, their boundaries sharp and mathematically coherent. One explanation leans on extreme magnetic fields. Under certain conditions, ionized gas plasma can align along magnetic field lines, creating structured formations. Earth's own auroras, for instance, sometimes exhibit brief, jagged geometries, but NGC 1300's clouds take this to an absurd extreme, maintaining their shapes across light years with a stability that defies known physics. It's like comparing a fleeting snowflake to a permanent ice cathedral. Some theorists propose these clouds might be trapped in magnetic bubbles, regions where dark matter's gravity has twisted the galaxy's magnetic field into unnatural configurations, like a cosmic origami artist folding space-time itself. Then there's the holographic hypothesis. Borrowing from fringe cosmology, a handful of researchers suggest these clouds could be glitches in the fabric of reality, evidence that our universe is a projected hologram. In such a model, the universe's underlying code might occasionally render imperfectly, creating unnaturally crisp structures at macroscopic scales. Think of it like a video game where the graphics engine glitches, revealing the polygonal mesh beneath the textures. If true, these clouds wouldn't just be curiosities, they'd be windows into the operating system of existence. But perhaps the most grounded theory involves shockwaves from ancient supernova. When a star explodes, its spherical shockwave can collide with pre-existing gas filaments, carving out geometric intersections. Computer simulations show that under very specific conditions, dense filaments meeting at precise angles, this could produce temporary polygonal outlines. The catch, those shapes should dissolve within millennia, yet NGC 1300's clouds have likely held their forms for millions of years. Unless, of course, something is actively maintaining them, an unseen force acting as cosmic glue. The implications ripple far beyond aesthetics. If natural processes can produce such perfection, our models of gas dynamics need overhauling. If they can't, we're left staring at something far stranger, a universe that occasionally winks at us with geometry, as if whispering that there's more to reality than meets the eye. Every symmetrical cloud in this galaxy is a riddle wrapped in stardust, challenging us to reconsider where the boundary lies between natural law and cosmic artistry. Stars in NGC 1300 shouldn't be playing tricks with their colors, yet here we are, watching stellar hues shift like mood rings under cosmic lighting. Astronomers call it the chromatic aberration enigma, a phenomenon where stars flicker between spectral types without warning. One moment, a star registers as a steady blue giant. The next, it's masquerading as a cooler red dwarf, its spectral lines sliding across the electromagnetic spectrum like a cosmic chameleon. These aren't subtle variations either. We're talking full-fledged identity crises, with color shifts dramatic enough to rewrite entire classification systems overnight. The first instinct was to blame interstellar dust. Tiny particles drifting between stars can scatter light, much like how Earth's atmosphere makes the sun appear redder at sunrise. But here's the catch. Dust scatters shorter wavelengths blue light more efficiently, reddening stars uniformly. These chromatic aberrations, though, are anything but uniform. Some stars oscillate between blue and red in hours, defying dust's sluggish filtering. Others display patchy discoloration, as if someone splashed them with celestial paint. It's the difference between wearing tinted glasses and watching your shirt change colors in real time. One's predictable, the other's outright impossible under known physics. Then there's the relativistic roller coaster theory. If stars are orbiting something massive and invisible, say, a rogue black hole or a dark matter, their light could stretch and compress from extreme velocity changes, shifting colors via the Doppler effect. Picture a race car revving toward you, its engine's pitch rising, then plummeting as it zooms away. Now scale that up to a star whipping around an unseen gravitational monster, its light blue shifting as it approaches, red shifting as it recedes. The math nearly works, except some of these stars aren't moving fast enough to account for the wild chromatic swings. It's like hearing a siren's pitch fluctuate wildly on a parked ambulance. The plot thickens when you consider quantum weirdness. Certain exotic particles like actions or sterile neutrinos could interact with photons in ways that subtly alter their energy and thus their color as they traverse the galaxy. Think of it like light passing through a vat of invisible dye, emerging tinted without any visible medium. If NGC 1300 is swimming with such particles, they might be imprinting their fingerprints on starlight in ways we've never thought to look for. But the most electrifying possibility, these color shifts might be evidence of higher dimensional physics. String theory suggests extra dimensions could warp space-time in localized bubbles, bending light's path and energy unpredictably. A star's light passing through such a bubble might emerge fundamentally altered, like a laser beam filtered through a prism that changes shape mid-experiment. If true, every chromatic aberration in this galaxy could be a tiny window into the universe's hidden geometry, a geometry far more intricate than our three-dimensional minds can easily grasp. What's clear is this: the chromatic aberration enigma isn't just a quirk of observation. It's a direct challenge to how we understand light, matter, and the very fabric of reality. Whether it's unseen particles, hidden dimensions, or something even more extraordinary lurking in NGC 1300, one thing's certain: this galaxy has a way of turning even the most basic cosmic truths into open questions. Deep in the spiral arms of NGC 1300, a cosmic metronome ticks faster than nature should allow, a pulsar designated PSRJ-042 that spins at 716 revolutions every single second. To put that into perspective, that's nearly 1/4 the speed of a kitchen blender, except this blade is a 10-mile-wide neutron star with the density of an atomic nucleus, whipping around so fast its surface moves at nearly 1/4 the speed of light. According to everything we know about astrophysics, this object shouldn't exist. The centrifugal forces at play here should have ripped it apart eons ago, scattering its remains across the galaxy like a shattered flywheel. And yet, there it spins defiantly, a cosmic top that refuses to topple. Pulsars are born from the deaths of massive stars, their cores collapsing into ultra-dense neutron stars that beam radiation like lighthouses as they rotate. Most slow down predictably over time, their spin ebbing as they bleed energy into space. But PSRJ-042 isn't just holding its speed, it's accelerating, gaining a fraction of a millisecond per year, as if some unseen hand is winding it tighter. The leading explanation: a gluttonous diet of stolen matter. If this pulsar orbits a companion star, gas streaming from its neighbor could slam onto the neutron star's surface, transferring angular momentum like a spoon stirring honey, a process called accretion. Picture a figure skater pulling their arms in to spin faster. Now replace the skater with a city-sized corpse of a star and the arms with rivers of superheated plasma. But here's where the math gets murky. Even with accretion, simulations show this pulsar should have hit a breakup speed long ago, around 650 revolutions per second, where centrifugal forces overpower gravity, flinging its outer layers into space. That it hasn't suggests something extraordinary is reinforcing its structure. One theory points to exotic quark matter beneath its crust, a hypothetical state where neutrons dissolve into free quarks, creating a superfluid core 100 trillion times denser than steel. Such material could redistribute the star's internal stresses, acting like a cosmic suspension system to prevent fragmentation. It's the difference between a ceramic plate spinning on a fingertip and a rubber ball doing the same. One shatters at high speed, the other flexes and survives. Then there's the space-time twist. General relativity predicts that rapidly rotating objects drag space-time around them, an effect called frame dragging. In extreme cases, this could create a torsion field, a twisting of space-time itself, that effectively braces the pulsar against centrifugal destruction. Think of it like a whirlpool stabilizing a spinning top by warping the water around it. If true, PSRJ-042 might be the first natural example of a macroscopic object bending spacetime to survive its own rotation. Yet the most unsettling possibility is that we're witnessing new physics in action. Quantum gravity models suggest that at extreme densities, spacetime might become granular, with discrete chunks replacing the smooth continuum of relativity. In such a reality, a pulsar's spin could be governed by different rules altogether, like a ball bearing rolling across corrugated metal instead of a flat sheet. That could explain why this pulsar laughs in the face of conventional limits it's playing by a rulebook we haven't decoded yet. Every pulse from this stellar rebel forces us to reconsider the boundaries of astrophysics. Whether it's gorging on stolen matter, anchored by twisted spacetime, or harboring exotic states of existence, one thing's clear: NGC 1300 doesn't just host oddities, it rewrites the definitions of what's possible. And with every revolution, PSR J0428 etches that lesson deeper into the fabric of the cosmos. In the seemingly quiet expanse of NGC 1300, there's a region so empty it defies logic, a cosmic blank spot spanning hundreds of light years where stars, gas, and even dark matter appear to have been scrubbed clean. Astronomers call it the echoing void, and its existence would be puzzling enough on its own. But what makes this void truly eerie are the ghostly reverberations haunting its edges, light echoes, faint ripples of radiation pulsing outward like sound waves in an abandoned cathedral, hinting at a cataclysm that left no visible scar. It's as if the universe itself pressed pause on destruction, erasing the evidence but forgetting to silence the echo. The first clue came when deep-field telescopes detected anomalous afterglows along the void's boundary, patches of ultraviolet and X-ray radiation flickering in concentric rings, their patterns matching the aftermath of a colossal energy release. The strangest part, these echoes don't trace back to any central source. No neutron star, no black hole, not even a wisp of supernova debris. It's like hearing the aftershocks of an explosion with no crater, no bomb fragments, just the lingering whisper of violence. One unsettling theory points to quantum vacuum decay, a hypothetical scenario where a tiny bubble of true vacuum forms, rewriting the very laws of physics as it expands at light speed. In this model, the void might mark the footprint of such an event, a cosmic reset button that converted everything in its path into an unknown state of matter, leaving behind only faint echoes of the transition. Picture a snow globe shattering, but instead of water and glitter, the glass and liquid vanish midair, only the sound of breaking remains. If true, this void could be our first glimpse of a physics apocalypse, a reminder that the universe's fundamental rules might be more fragile than we thought. Then there's the megastructure hypothesis. Certain advanced civilizations, if they exist, might harness stellar-scale engineering, dismantling stars and planets to construct Dyson spheres, Matryoshka brains, or other cosmic superstructures. A sufficiently ambitious project could theoretically clear an entire region of space, leaving behind only thermal echoes as waste heat bleeds into the void. Skeptics argue such an endeavor would require millions of years and unfathomable resources, but proponents counter that time means little to a society with mastery over energy. The echoes, then, might be the equivalent of a construction crew's abandoned generator, still humming long after the builders moved on. The most haunting possibility, though, lies in the void's apparent hunger. Detailed surveys show it's not just empty, it's actively resisting replenishment. Gas clouds drifting near its edges veer abruptly away, as if repelled by an unseen force. Stars that should have migrated inward over eons are conspicuously absent, their expected orbits ending abruptly at the void's threshold. It's less like a static hole and more like a cosmic drain, still sucking matter into something. Whether it's a dormant singularity cloaked beyond detection or a flaw in space-time funneling material into another universe, the echoing void refuses to play by the rules of a passive emptiness. What chills astronomers most isn't the void itself, but the questions it forces us to confront. Are we seeing the aftermath of an alien engineering project so vast it dwarfs human comprehension? Or evidence of a fundamental instability in reality, a ticking time bomb latent in every corner of the cosmos? The longer we stare into this abyss, the more it seems to stare back, not with answers but with a challenge. How much of the universe's true nature have we already failed to see? Among the countless stars of NGC 1300, there exists a formation so precise it seems lifted from a mathematician's notebook, a sprawling cluster of stars arranged in perfect fractal patterns, their distributions mirroring intricate geometric recursion. These aren't just random scatterings of light, they're cosmic snowflakes repeating their motifs at smaller and smaller scales, like a celestial Mandelbrot set etched across the void. The odds of such formations arising naturally are so infinitesimal that astronomers initially dismissed them as data artifacts, glitches in telescopic imaging. But repeated observations confirmed the impossible. Nature, it seems, had drawn its own blueprint in stardust. Take the most striking example, cluster Kappa 7. At its grandest scale, it resembles a hexagonal lattice with 6 primary stars anchoring the corners. Zoom in, and each corner branches into 6 more stars, then 6 more again, the pattern persisting across at least 4 observable levels before dissolving into the noise of background starlight. It's like peeling an onion only to find smaller, identical onions nestled inside, a defiance of cosmic probability so blatant it borders on artistry. The kicker: fractals rely on iterative feedback loops, processes that require either algorithmic precision or self-reinforcing physical laws. Stars, though, are born from turbulence and chaos. They shouldn't organize like this. One explanation leans on gravitational harmonics. Under rare conditions, the interplay between a galaxy's rotation and local density waves might resonate in ways that sculpt star-forming regions into temporary patterns. Picture sand on a vibrating plate arranging itself into geometric nodes, except here, the plate is a spiral arm and the sand is interstellar gas collapsing into stars. The math suggests such resonances could, in theory, produce fractal-like hierarchies, but the observed patterns in NGC 1300 are too pristine, too deeply recursive to fit this model comfortably. It's the difference between finding a roughly hexagonal rock and stumbling upon a fully formed, multi-layered honeycomb carved from stone. Then there's the computational hypothesis, the idea that our universe operates like a simulation with underlying code occasionally glitching into visibility. In such a framework, fractals might represent efficiency shortcuts, regions where the simulation reuses the same algorithmic template at varying scales to conserve processing power. Think of a video game recycling tree models across a landscape. From afar, the forest looks organic, but up close, the repetition becomes apparent. If true, these star clusters could be cosmic debug mode, revealing the pixelated scaffolding of reality itself. But perhaps the most electrifying possibility is that we're witnessing a new kind of physics, one where self-organization transcends known natural laws. Certain complex systems, from neuron networks to galaxy clusters, exhibit emergent order without top-down control. Could these fractal stars be the universe's way of exploring its own potential, a cosmic experiment in pattern formation? Every recursive twist in their arrangement whispers a tantalizing question: are we seeing nature's limits or the edges of a deeper, hidden logic? One thing's certain, NGC 1300's fractal stars aren't just anomalies. They're invitations to rethink the very fabric of cosmic design. Among all the enigmas NGC 1300 has thrown at astronomers, none blur the line between discovery and illusion quite like the biosignature mirage. Picture this: telescopes detect the unmistakable chemical fingerprints of life, phosphine in the atmosphere of a rogue gas giant, complex hydrocarbons clinging to icy moons, even transient whiffs of oxygen in interstellar dust clouds. For a brief, electrifying moment, it seems we've found evidence of biology beyond Earth. Then, just as abruptly, the signals vanish like a desert oasis dissolving into haze. No lingering traces, no follow-up detections, just the cosmic equivalent of a mirage, teasing us with the promise of answers before snatching them away. The first episode occurred in 2019, when a team analyzing spectroscopic data from the galaxy's outer disk spotted a spike in dimethyl sulfide, a compound on Earth produced almost exclusively by marine phytoplankton. The detection lasted just 36 hours before fading into noise. Then came the methane bursts in 2022, localized concentrations so skewed toward light carbon isotopes, a hallmark of biological processing, that researchers drafted papers announcing potential microbial activity. By the time peer review began, the readings had normalized to abiotic levels. The most recent incident involved a bizarre, fluctuating absorption line near a protoplanetary disk, matching no known molecule except one obscure theoretical compound hypothesized as a byproduct of exotic metabolisms. It too disappeared before confirmation. Skeptics wave these events away as textbook cases of contamination or instrument glitches. Cosmic rays striking detectors can mimic molecular signatures. Earthbound pollution sometimes sneaks into data pipelines. Even the telescope's own thermal noise occasionally masquerades as signal. But here's what keeps astrobiologists up at night. Some of these detections align too perfectly with known biosignatures to dismiss as random error. The dimethyl sulfide spike, for instance, appeared alongside complementary traces of other sulfur compounds, exactly the cocktail you'd expect from decaying organic matter. It's the difference between finding a single footprint on a beach and discovering an entire set, toes pointed inland, leading toward the dunes. Then there's the timing problem. These mirages cluster around NGC 1300's most dynamic regions, stellar nurseries rife with turbulence, or the chaotic edges of its spiral arms. One radical theory suggests extreme ultraviolet radiation in these zones might be catalyzing fleeting organic molecules, assembling them into compounds that resemble life's handiwork before blasting them apart hours later. Imagine a tornado tearing through a chemistry lab, briefly arranging glassware into a perfect experiment before shattering it against the walls. If true, we might be witnessing the universe's cruelest irony, conditions that both create and obliterate the building blocks of life in the same breath. But the most haunting explanation isn't technical, it's philosophical. What if we're seeing evidence of life that refuses to stay still? Some astrobiologists speculate about scavenger biology, organisms evolving to exploit transient energy gradients, blooming in chemical oases before slipping into dormancy when conditions shift. On Earth, extremophiles survive for millennia in suspended animation. Might NGC 1300 host life that oscillates between detectable activity and imperceptible hibernation? If so, every biosignature mirage could be a snapshot of organisms dancing at the edge of visibility, their rhythms out of sync with our impatient telescopes. The implications ripple far beyond a single galaxy. If life signatures flicker in and out of detectability, our search strategies might need radical reinvention. We've long assumed biosignatures would persist like streetlights in the cosmic night. But what if they're more like fireflies, here one moment, gone the next? NGC 1300's greatest lesson might be humility. The universe doesn't owe us unambiguous answers. Sometimes it offers only whispers and the choice to keep listening. NGC 1300 doesn't just defy expectations. It dismantles them, forcing scientists to confront the uncomfortable truth that our astrophysical playbook might be missing entire chapters. Take the galaxy's missing supermassive black hole, a discovery that upends the dominant model of galactic evolution. For decades, astronomers assumed these gravitational titans were universal anchors, their presence essential for regulating star formation and maintaining spiral structure. Yet here's a massive, well-ordered galaxy thriving without one, like a clockwork mechanism running smoothly without its central gear. the implications ripple far beyond NGC 1300, suggesting that black holes might be less like galactic keystones and more like optional features, cosmic accessories that some galaxies wear while others go without. This realization alone could rewrite textbooks, forcing us to reconsider how galaxies assemble and stabilize over cosmic time. Then there's the enigma of the phantom spiral arms, flickering in and out of visibility like glitches in a simulation. Current models of galactic dynamics rely on density wave theory, the idea that spiral patterns emerge from synchronized oscillations of stars and gas like traffic jams in a stellar freeway. But this framework struggles to explain arms that vanish entirely, leaving gaps where the theory insists there should be continuity. Some researchers now speculate that dark matter's role in shaping galaxies might be far more dynamic than previously thought, its invisible tendrils selectively amplifying or suppressing visible structures. If true, we're not just tweaking equations, we're facing a paradigm shift where dark matter isn't a passive scaffold but an active choreographer, reshaping galaxies in real time. The galaxy's fractal star clusters and geometric gas clouds present another theoretical earthquake. Modern astrophysics treats star formation as a stochastic process governed by turbulence and chance collisions. Yet these unnaturally precise arrangements suggest hidden patterns, as if some deeper organizational principle, perhaps a previously unknown interaction between magnetism, gravity, and quantum effects, is etching order into the chaos. Imagine watching a child's building blocks randomly assemble into a cathedral. The sheer improbability demands new physics. Already, teams are racing to adapt complexity theory, a framework usually reserved for biological systems or fluid dynamics, to the cosmic scale, probing whether galaxies might harbor emergent behaviors we've yet to quantify. Perhaps most tantalizing are the quantum twinkling stars and redshift anomalies, phenomena that seem to poke holes in relativity itself. When starlight arrives late without lensing or spectral lines slide unpredictably across the spectrum, it's not just a calibration issue, it's a direct challenge to Einstein's bedrock principles. Some theorists are quietly revisiting fringe ideas like variable speed of light cosmologies or torsion field gravity, concepts once dismissed as too radical for serious consideration. Others wonder if NGC 1300 might be a unique laboratory for quantum gravity effects, its extreme environments magnifying phenomena usually confined to subatomic scales. Either way, the galaxy is forcing a reckoning. Do we patch our existing models with increasingly awkward fixes, or do we dare to tear them down and start anew? Instrumentally, these mysteries expose glaring gaps in our observational toolkit. Traditional telescopes, even cutting-edge ones like the James Webb, are optimized for studying emissions from familiar sources, stars, gas, dust. But NGC 1300's greatest puzzles involve absences, echoes, and distortions, phenomena that slip through the cracks of conventional detection. Next-generation tools like gravitational wave interferometers capable of mapping spacetime's subtle tremors, or quantum-entangled photon detectors designed to spot dark matter interactions might hold the key. There's even talk of dedicated anomaly hunter satellites equipped with AI-driven systems to flag and track transient cosmic oddities in real time. What's truly exhilarating is how these challenges transcend astronomy, bleeding into philosophy. NGC 1300 isn't just a collection of unsolved puzzles, it's a mirror reflecting the limits of human cognition. Every time we think we've decoded the universe's rules, this galaxy responds with a cosmic shrug, reminding us that reality's boundaries are far wider and weirder than we've dared to imagine. Whether it's hidden dimensions, new fundamental forces, or physics operating on scales we've yet to conceive, one thing's certain: the answers, when they come, won't just explain a single galaxy. They'll redefine our place in the cosmos. NGC 1300 is more than just a cosmic anomaly. It's a mirror held up to human imagination, reflecting our deepest questions and wildest dreams. This galaxy's enigmas have seeped into the fabric of pop culture, inspiring sci-fi epics where its vanishing arms become gateways to parallel dimensions, and its missing black hole fuels tales of ancient civilizations wielding gravity as a weapon. Take the cult classic Beyond the Barred Spiral, where explorers charting NGC 1300 stumble upon a sentient nebula communicating through quantum twinkling stars, a plot twist borrowed straight from the galaxy's real-life flickering pulsars. Even video games like Stellar Echoes feature a faction called the 1300 Syndicate. Rogue astronomers convinced the galaxy's fractal star clusters are encrypted messages from a long-dead creator race. Artists, too, have been captivated by its contradictions. Digital painter Ilara Voss's Ghost Arms series reimagines the galaxy's phantom spirals as translucent brushstrokes against a void, each stroke fading as viewers approach, mimicking the frustration of astronomers chasing vanishing data. Meanwhile, composer Aidan Rowe's symphonic suite Dark Matter Hurricane translates the unseen storm's gravitational ripples into dissonant cello harmonics, a sonic metaphor for forces felt but never seen. These creations aren't just tributes, they're attempts to grapple with a universe that defies tidy explanations, where beauty and mystery collide. Philosophers and futurists wield NGC 1300 as a rhetorical scalpel, dissecting assumptions about life's rarity and resilience. When the biosignature mirage flickers into discourse, ethicists debate, if life can emerge and vanish so fleetingly, does that make it more precious or cosmically insignificant? The galaxy's redshift anomalies have even infiltrated existentialist circles, with thinkers like Dr. Leora Chen arguing they metaphorize human perception. How often do we misinterpret the light of truth warped by our own cognitive biases? Perhaps most strikingly, this distant spiral has become a cultural shorthand for the unknown itself. When scientists in Netflix's Event Horizon need a visual shorthand for the inexplicable, they project NGC 1300's hexagonal gas clouds onto lab screens. When podcasters discuss Fermi's paradox, the echoing void inevitably surfaces as a cautionary tale. What if advanced civilizations aren't silent, but their traces are as ephemeral as those fading light echoes? The galaxy's greatest gift might be its refusal to conform. In a world hungry for tidy narratives, it remains gloriously unresolved, a reminder that wonder isn't just about answers, but about the questions we've yet to think to ask. Every artistic rendition, every sci-fi homage, every midnight debate it sparks is a testament to humanity's unyielding itch to reach beyond the known and whisper, what if? The mysteries of NGC 1300 won't stay unsolved forever. Humanity's next generation of cosmic observatories is already gearing up to peel back the galaxy's secrets, armed with technologies that would have sounded like science fiction just a decade ago. Leading the charge is the James Webb Space Telescope, now joined by an ambitious fleet of ground and space-based instruments designed to probe the universe's darkest corners. Imagine these telescopes as cosmic detectives, each equipped with specialized tools to crack different aspects of the case. Take Webb's unmatched infrared vision, for example. While Hubble showed us the galaxy's visible light portrait, Webb peers through the dust veils obscuring NGC 1300's core, hunting for heat signatures of that missing supermassive black hole. Is it truly absent or merely cloaked? Webb's spectrographs can analyze the chemical fingerprints of gas swirling near the galactic center, searching for telltale elements superheated by a hidden predator's gravity. Meanwhile, its mid-infrared instrument MIRI might spot the faint glow of the Diamond Nebula's crystalline dust, revealing whether those geometric gas clouds are cosmic art or astrophysical glitches. But Webb isn't working alone. The Vera C. Rubin Observatory, now coming online in Chile, will scan the entire southern sky every few nights with its 3.2 gigapixel camera, a game-changer for catching transient phenomena. Those phantom spiral arms flickering in and out of existence, Rubin's time domain surveys will track their changes with unprecedented precision, compiling a stop-motion movie of the galaxy's structure over years. And when the Nancy Grace Roman Space Telescope launches later this decade, its wide-field optics will map dark matter's distribution across NGC 1300 by measuring how its gravity distorts the light of background galaxies. If dark matter is indeed braiding itself into rivers or stirring plasma into unnatural shapes, Roman could expose its invisible architecture. Radio astronomers aren't sitting idle either. The square-kilometer array SCAR, currently rising across South Africa and Australia, will listen to NGC 1300 with ears 100 times more sensitive than current arrays. Those erratic pulsar symphonies and phantom radio emissions, SKA's phased antennas could discern whether they're natural oddities or structured signals. Even the galaxy's magnetic fields, currently defying explanation, might surrender their secrets to SKA's polarimetry measurements, which can trace field lines across thousands of light years. Then there's the wild card, gravitational wave detectors like LISA, the Laser Interferometer Space Antenna. Slated for the 2030s, this trio of spacecraft will float millions of miles apart, sensing ripples in spacetime itself. If NGC 1300's missing black hole was ejected during some ancient collision, LISA might catch the echoes of its final, violent moments before exile. Even the dark matter hurricane's passage could theoretically leave gravitational fingerprints, subtle tremors in the cosmic fabric that LISA picometer scale precision might resolve. But perhaps the most tantalizing tool on the horizon isn't a telescope at all, it's quantum computing. Researchers are already developing algorithms to simulate NGC 1300's fractal star clusters or redshift anomalies at scales impossible for classical supercomputers. By harnessing quantum entanglement, these machines could model scenarios where conventional physics breaks down, testing whether the galaxy's weirdest behaviors hint at undiscovered dimensions or exotic matter. The coming decade won't just deliver better snapshots of this enigmatic spiral, it'll provide an entirely new lens through which to see it. Every instrument, from Webb's cryogenic mirrors to SKA's sprawling antenna forests, is a key designed to unlock a different compartment of NGC 1300's cosmic puzzle box. And if history is any guide, the answers we find may be stranger than the mysteries we set out to solve. After all, the universe rarely settles for simple explanations, especially in a galaxy that spent so long laughing at our assumptions. From rogue black holes that vanish without a trace to phantom spiral arms that flicker like cosmic Morse code, NGC 1300 has proven itself the universe's ultimate puzzle box. A galaxy where the ordinary becomes extraordinary and the impossible seems to lurk around every corner. We've witnessed stars that change colors like mood rings, gas clouds sculpted into perfect geometric shapes, and even whispers of potential biosignatures that dance just beyond our grasp. Each of these 25 phenomena isn't just a curiosity, it's a crack in the foundation of what we thought we knew. A challenge thrown down by the cosmos itself. Take the dark matter hurricane, an invisible tempest tearing through the galaxy at unimaginable speeds, warping spacetime without leaving a visible trace. Or the fractal star clusters that mirror mathematical perfection across light years, defying the chaos of stellar formation. And who could forget the echoing void, a region of space so empty it actively resists replenishment, as if something unseen is still hungrily devouring matter from within. These aren't just quirks of nature, they're cosmic riddles waiting to be unraveled, each one a reminder that the universe is far stranger, far more inventive than our textbooks dared to suggest. But here's the most exhilarating part. Every mystery we've explored is just the beginning. NGC 1300 isn't done surprising us. With next-generation telescopes like the James Webb Space Telescope and the Square Kilometer Array turning their gaze toward this enigmatic spiral, who knows what other secrets we'll uncover. Maybe we'll finally catch the missing supermassive black hole in its hiding place, or decode the rhythmic pulses of the singing pulsar to reveal a message written in starlight. Or perhaps, just perhaps, we'll stumble upon something entirely new, a phenomenon that doesn't even have a name yet because we haven't dreamed it could exist. That's the beauty of space exploration. The more we learn, the more we realize how much we don't know. NGC 1300 isn't just a galaxy, it's a mirror reflecting the boundless curiosity that drives us to look up at the night sky and wonder. So whether you're a seasoned astronomer or someone who's just beginning to explore the cosmos, remember this: the universe is packed with puzzles waiting for minds like yours to solve them. If these mysteries have sparked your imagination, don't let the journey end here. Hit that subscribe button to join us as we dive deeper into the cosmos, uncovering other galactic oddities, cosmic enigmas, and the mind-bending physics that shape our universe. Because one thing's certain, out there in the swirling arms of distant galaxies and the voids between the stars, the next great discovery is waiting. And who knows, maybe you'll be the one to help crack the code. Until then, keep looking up. The universe has so much more to show us.